All right, so for this week's standard, you're doing IOD 603. And this is, again, about interpolating and extrapolating. Interpolate and extrapolate. So that's where you're predicting what happens in those. So the first one is you find the variables in the question. Then you determine the trend. Then you find the known values on inside or outside. And you make your prediction. So those are the steps you'll need. All right, number 1, based on the results of study 1, so I'm going to look at study 1, at a coefficient of friction at 0.3, a vehicle of stopping distance with 5.5 would most likely be traveling at which of the following velocities? So, a kinetic friction, coefficient of friction of 0.3, these are the values that we're going to look at. And then a stopping distance of 5.5 meters. So here we have these. And you're looking at these and how they relate to each other. So we have 21.3, 85.3, 21.7, 85.4, 86.1, and 21.6. And then looking at the velocities here. So for this one, the velocity is 40 when the stopping distance is around 21. And we need the stopping distance to be around 5. So if this is 5, how do these relate to each other? So that's like our x. So 21 and 5, that goes in by 4 almost. So we'll divide that by 4. So it's going to be 10-ish. And then you can also have them. So 5.5, a quarter of that. And then if you look here, what happens to the relationship for 80? So 40 to 80, it goes from 20 to 80 about. So if you're looking at that relationship, and then that's going to give you C is the closest in that relationship. Number 2. Based on the information given in figure 2, so I'm going to look at figure 2, how fast must the tungsten rod, and I'm talking about the tungsten rod, so that means I'm talking about this one. That's figure 1, launched in order to breach the opposite side of the steel wall. So, based on the information of figure 2, how fast must it be going to breach the other side of the steel wall? First, let's figure out what this means. 65 was launched into a 15 centimeter thick steel wall. The DOP was measured. So we need it to breach the other side, so that means it needs to be more than 15 centimeters. So this graph up to 15. This graph goes up to 10, so we need to find the slope of this line. So we pick 2 points to find the slope. So let's say we have 1809 and let's see where it's on a line. That's about 1305. So 9 minus 5 over this one, so 4 over, oh, it's rise over run, sorry. So 4 centimeters over 1800 minus 1300, so it's about 500. That's your slope that you're going up by. So plug it in for 15. Y equals mx plus b. This b is about, what, 0.5? 4 over 500. 15 equals, and then you're looking at that x. Right, so 14.5 times 500 divided by 4 is the x value that you're looking for. And if you do that math, number 2, we know it's going to be big. Oh, we didn't even have to. So greater than 2,500 meters per second, and we know it's for sure going to be greater than 1,800. And if that's another halfway up. So another halfway up, it's almost a full graph. So we can go ahead and say that the answer is going to be greater than 2,500. It's going to go way off our graph. All right, number 3. If a 120 centimeter long string were used in this experiment, the simple pendulum's calculated oscillation would most likely fall between which of the two values? So we don't have 120. Right? But what are these doing? With each oscillation, or with each length of the string, they're going up. Right here for 10 oscillations. So that means we also need to divide these by 10. So that's going to be 2.0. That's going to be 1.9, 1.7, 1.6, and so on, all the way down to 0.7. So where would 120 fall? And we know that it ends right about at 2.0. So we're going to say 2.08 if you look at the trends here, because these are about a difference of 20 or 15 anyway. A simple pendulum made with a 200-gram mass and a lightweight string has calculated oscillation period of 0.37 seconds. Based on the information presented in Table 2, approximate how long is the lightweight string? So the oscillation period is 0.37 seconds. So 0.37 goes right here in our trend, and as the length of the string goes down, this goes down. Now this is a difference of about 0.3, and that's about 12 again. So we're going to probably go down to there. So subtract about 12 centimeters from this. So for number 4, we're going to pick the smallest amount of centimeters. It's going to be A. All right, number 5. Based on Figure 1 and Table 1, one would expect the uncatalyzed reaction time for 9 milliliters of solution A with 1 milliliter of H2O at 2 degrees. So based on Figure 1 and Table 1, uncatalyzed reaction time, 9 milliliters of solution A. So these are the values that we need. So Figure 1 and Table 1. Solution A, we need the reaction time. That's the answer that we're looking for. It's 2 degrees Celsius, so that's going to be somewhere around here. And Table 1, 9 milliliters of solution A with 1 milliliter, that's about 20 seconds. It has that reaction time. And then this one is about, on the graph here, if you go to about 2 degrees Celsius, that's above 25, would be where that hits. So if we combine those values here, because this is the uncatalyzed. So if you're reading the blurb here, we have at least 20 seconds for the constant temperature of 25 degrees Celsius. Okay, it was 20 seconds at 25 degrees Celsius, which we know on this graph was about 15. But we're dropping it down to 2 degrees Celsius, so we see this trend is increasing. So that means the reaction time is going to be where it hits on the graph. So that gives us our answer, greater than 24 seconds.